Section 3.4, the chain rule. So consider taking the derivative of this function right here, square root of x cubed plus 1. Now the problem with this is we don't actually know how to take this derivative at this point because it's not a product. We're not multiplying two things together. It's not a quotient, so we can't use the quotient rule, the product rule. There's no sines or cosines. We can't do the trig rules. And it's not a straightforward power rule because we don't just have x cubed, we have an x cubed under a square root. So there's a few ways that would seem to make sense to do this. So if we think of f of x as x cubed plus 1 raised to the 1/2 power, so changing that square root into the fractional way, you could think, okay, maybe I'll take the derivative of that thing to the 1/2 power. So you bring the 1/2 down. So you would have f prime of x equals 1/2 x cubed plus 1 to the negative 1/2 power. So you're bringing the 1/2 down and subtracting 1 from the exponent. Or you could think, well, I'm going to leave the outer part the way it is to the 1/2 power, and I'll take the derivative of the inside part and just get the 3x squared to the 1/2 power, because the plus 1, that's just a constant, so it would turn to 0. Or you could do both. So that would be 1/2 times 3x squared to the negative 1/2 power. I take the derivative of that outer thing, and I also take the derivative of what's inside the parentheses. And which one of these is correct? Turns out none of them. All wrong. Every single one of them are bad and incorrect. And to understand the derivative of this function, you need to know a little bit more about composite functions. So a composite function is a function comprised of two functions. One of the functions is substituted inside the other function. So here, our outer function is square root of u, and our inner function is x cubed plus 1. So if you do f composed of g, that's g of x inside f, you're putting the x cubed plus 1 inside the f function, and you get the square root of x cubed plus 1. And that's what we want to take the derivative of. So our derivatives will involve these two functions, but in sort of a strange way. In particular, what you have to do is take the derivative of the outer function, just like we were doing, but you leave the inner function the way it is, and then you take the derivative of that inner function and multiply it on the outside. So in mathematical notation, we say the derivative of f of g of x is equal to f prime of g of x times the inner function, so that's the derivative of the outer function, evaluated at the inner function, and then we take the derivative of that inner function and multiply it on the outside. And there's also a way of writing this using Leibniz notation, which is that dy over dx is equal to dy over du times du over dx. And I will show both ways. Generally, people sort of think of the calculation in this form. It turns out this is a nice form for other calculations in the future as well, so it's good to know both ways. And we're not going to prove the chain rule, but we're going to show that it works with a example. So suppose f of u equals u squared and g of x equals 2x plus 1. If we wanted to find the derivative of f prime of g of x, we could do it two ways. First, we could figure that f of g of x is equal to 2x plus 1 squared, because I'm taking this 2x plus 1 and I'm putting it inside here in place of the u, and that gives me that squared. And I can square this out. That's 2x plus 1 times 2x plus 1. I could do the product rule on this, or I could just multiply it out. 4x squared plus 4x plus 1. And now when I take the derivative of that, it's just the derivative of that polynomial, so the 2 comes down, I get 8x plus 4. And that's my answer. Now using the chain rule says that the derivative of f of g of x is equal to f prime of g of x times g prime of x. And let's see, I've got my f of u here, so if I do f prime of u, that's equal to 2u, the 2 just comes down, and then g prime of x is equal to just 2, because the 2 comes from the 2x and the 1 goes to 0. So what is f prime of g of x? That means I'm plugging g of x into this function right here. So f prime of g of x is equal to 2 times g of x, and g of x is 2x plus 1. So that's 2 times 2x plus 1. And then we multiply that by g prime of x, which we just found to be 2. This is 4 times 2x plus 1, or 8x plus 4. And these are the same. And that's our confirmation that the chain rule actually works, because it doesn't matter if I do it this way or that way. In general, you won't actually be able to sort of multiply something out, and you'll have to use the chain rule in most instances. So let's do example 1, and I'm going to do it 2 different ways using the Newton's notation and Leibniz's notation. So first let's do it the way we did the one up there. We want to write square root of x cubed plus 1 as f of g of x. So the way we're going to do that is we'll say f of x is equal to square root of x, and g of x is equal to x cubed plus 1. So the g of x is my inner function, that's inside the square root, and the f of x is my outer function, that's that square root there. And then we take derivatives. This is going to be 1/2 x to the negative 1/2, and g prime of x is equal to 3x squared. So f prime of g of x times g prime of x, that's what we get when we take the derivative. This is, I guess I could say this is the derivative of f of g of x. And f prime is 1/2 x to the negative 1/2 power, but I don't want f prime of x, I want f prime of g of x. So I'm taking, in place of this x here, I'm plugging in g of x, and my g of x is x cubed plus 1. And now I'm raising that to the negative 1/2 power. And then I multiply that by g prime of x, which is 3x squared. And that's my answer. Now if I wanted to use Leibniz notation, I would think about it this way. I would say y is equal to x cubed plus 1. And I can think of that as y being the square root of u, where I let u equal x cubed plus 1. So I can now take the derivative of this thing, dy du, that's 1/2 u to the negative 1/2 power, and I can take du over dx, and that's 3x squared. So the derivative of this is 3x squared, derivative of that is 1/2 u to the negative 1/2 power. And the chain rule, using Leibniz notation, says that dy dx is equal to dy over du times du over dx, so that's just 1/2 u to the negative 1/2 power times 3x squared. And this is perfectly fine, but I want everything in terms of x at the end of the day, so in place of this u, I'm going to substitute in x cubed plus 1. 1/2 x cubed plus 1 to the negative 1/2 power, and that's all times 3x squared. And notice I get the same thing here and here. And I'm going to do it one more way real quick, and this is just, when you get better at the chain rule, this is the way you're actually going to do it, as sort of in your head. When I see the derivative of the square root of x cubed plus 1, I think, well, that's the derivative of x cubed plus 1 to the 1/2 power. And how do I take that derivative? I first take the derivative of the outer function. Outside the parentheses, I've got that exponent of 1/2. So I take that derivative, the 1/2 comes down, the new exponent is negative 1/2, and I leave the inside the exact same, and then I chain rule, and I take the derivative of that x cubed plus 1, and that gives me my 3x squared. And that's it. Okay? So once you get better at it, this is what you're going to be doing right here. You don't need to have all this fancy notation, but for the time being, it might help to break it into different pieces until you fully understand it. And the last thing I wanted to mention is this can actually be simplified. So the 3x squared would go on top. The 2 goes on the bottom because you got the 1/2, and then this to the negative 1/2 power puts the square root of x cubed plus 1 on the bottom. And this is a nicer way of writing it. Both of these are correct, however.